Welcome back. Lesson 2, Applications of Propositional Logic. Introduction. Logic has many important applications to mathematics, computer science, and other disciplines. Human language can be ambiguous. Translating sentences into compound statements removes the ambiguity. For example, you can enter the college if you have a BCC identification card or a driver's license. Okay. Let B represents the proposition you have a BCC identification card. It may be true or false. We don't know that a priori. Okay. But that's your proposition. Let D represent you have a driver's license. Okay. And C represent the proposition you can enter the college. Then what does this say? If you have BCC identification card or a driver's license, B or D, then you can enter. So B or D, that's the hypothesis, implies your conclusion. You can enter the college. So this entire sentence is represented in this particular expression where B, D, and C are clearly defined. Okay. So here are two examples. You might want to try breaking these statements down to simple propositions and writing an expression, compound expression. You can go to the movies if you complete your homework and cleaned your laundry. That's one example. Another example. You cannot drive if you are younger than 16 years of age unless you live in Mars. This is an interesting one. You might want to try these two. Okay. System specifications. Requirements in natural language can be translated to produce precise and unambiguous specifications. For instance, the system cannot save your files when it is out of memory. Here, so this is your sentence. Let P be the system saves your files. So cannot means not P. Q, the system has memory. So out of memory is not Q. So when not Q, not P happens, you see. So not Q implies not P. That's the translated specification. System specifications should be consistent. That is, they should not contain conflicting requirements that could be used to derive a contradiction. Okay, so you don't want something contradictory. Are these system specifications consistent? Okay, for example here, whenever the system software is being upgraded, users cannot access the file system. If users can access the file system, then they can save new files. If users cannot save new files, then the system software is not being upgraded. See whether this makes sense. If there is a contradiction, then it is not consistent. Give it a few minutes and tell yourself, does it make sense? System software is being upgraded, so users cannot access the file system. If users can access the file system, then they can save new files. Users cannot save new files, then the system software is not being upgraded. So check this whether it makes sense to you, whether it's consistent or not. Okay, it's a nice exercise. Boolean searches. Logical connectives are used in searches of large collections of information. Because these searches employ techniques from propositional logic, they are called Boolean searches, and is used to match records that contain both of the two search terms, or is used to match one or both of the two search terms. Not, sometimes written and not, is used to exclude a particular search term. For instance, using Boolean searching to find web pages, we can look up Indiana and university. We could also try Indiana or New York and university. Now try Indiana or York, so together, and university, but not new. In Google, the word not is replaced by the symbol dash. Okay, you might want to try this on your web search. Okay, so here are examples of Boolean searches. Logic puzzles. Puzzles that can be solved using logical reasoning are called logic puzzles. The following puzzle was posed by well-known logician and philosophy professor Dr. Raymond Smilin. An island has two kinds of inhabitants: knights, who always tell the truth, and their opposites, knaves, who always lie. Oh, this is a beautiful one. You might want to try. You encounter two people, A and B. What are A and B if A says B is a knight and B says the two of us are opposite types? All right, so this is a nice exercise. If A is a knight, then B is a knight. You understand? A knight will always tell the truth. So if A is a knight and if A is saying B is a knight, then they are both knights. In which case B has to speak the truth also. So if B says the two of us are opposite types, then that's false because they are both knights. Therefore, consider the option when A is a knave. Knave will always lie. So A says B is a knight. That means A has lied. In other words, B is a knave. Okay? So if B is a knave and B says the two of us are opposite types, so B has to always lie. We are of opposite types, so B, because he is a knave, he has to lie. So they have to be of the same type. So B is a knave and A is a knave. That's the correct answer. Here is another puzzle, the muddy children puzzle. A father tells his two children, a boy and a girl, to play in their backyard without getting dirty. However, while playing, both children get mud on their foreheads. When the children stop playing, father says at least one of you has a muddy forehead, and then asks the children to answer yes or no to the question. Do you know whether you have a muddy forehead? The father asks this question twice. What will the children answer each time this question is asked, assuming that a child can see whether his or her sibling has a muddy forehead, but cannot see his or her own forehead? Assume that both children are honest and the children answer each question simultaneously. Okay? So the father is asking the kids simultaneously, do you know whether you have a muddy forehead? Okay? And the father is going to ask this question twice. Presumably the first time he asks, they both say, I don't know. They are not allowed I don't know. They are allowed yes or no. So argue this and see whether it makes sense to you. We'll discuss this in class, or you may argue it for yourself. All right. Next comes to logic circuits. In 1938, Claude Shannon, in his MIT master's thesis, observed that propositional logic can be applied to the design of computer hardware. A logic circuit or digital circuit receives input signals P1 through Pn. Each a bit is binary digit, either 0, which is an off, or 1, which is an on. Okay. So these are input signals. So either they are 0 or 1, and produces output signals S1 through Sn, again each a bit. In this section, we will restrict our attention to logic circuits with a single output. Okay, so you get a lot of input, but the final output is single. In general, digital circuits may have multiple outputs. So here are basic logic gates. P, here is negation, negative P. That symbol is for negation. P and Q, this is OR, P or Q. P, Q, and this is the AND symbol, P and Q. So these are the gates. Negation gate is called inverter. Disjunction gate is called OR gate. Conjunction gate is called AND gate, and these are the symbols. All right. Here are complicated digital circuits, right? 3 basic circuits, you have gates, right? P, Q, R. So let's look at what's happening first. R is getting negated, Q is getting negated. P and Q. So there is a conjunction. Whatever you get, P and negative Q, you are then taking a disjunction with negative R. So that's your combinatorial circuit. Here is a more complicated combinatorial circuit for this expression. Okay, logical expression. So this completes lesson 2, by the way. We'll continue lesson 3 in our next video.